Hello everybody, I will start my today another live coding session. So in my today's session, I will solve this question. Kth largest element in an array. And for this question, I will introduce four approaches. Okay. So in this question, I'm giving an integer array nums and integer k. And I will return the kth largest element in an array. Note that it is the kth largest element in the sorted order, not the kth distinct element. Can you solve it without sorting? Okay, so as shown in the example one, um, yep, my input is nums array, which is an integer array, and I will be given an integer k, in this case 2. And my task is to return the second largest element in an array. So the output should be an integer. In this case, 5, so I will return 5. Okay. Yep. And as I can see from the constraint, k is 1 or more, and it is equal or less than nums length. So this means that I can always find the kth element to be returned. Okay. Also, yep. I just wanted to take care that, yep. For example, in the example 2, fourth largest element, 6 is the largest one, and 5 is the second and third, and 4 is the fourth largest element. So if there is a tie, like 5 and 5, it will consume one position. So, or I should say one rank. So it doesn't go like 6 is the largest, and second largest is 5, and third largest is 4, and first largest is 3. It doesn't go like that. Okay, so that being said, I will introduce 4 approaches. The first approach is sorting. So this is a quite simple approach and quite intuitive. So I just have to sort the array, and then I will return the, I mean, yep. Oh, so I will sort the array in a descending order. Then I will return the fourth largest element, fourth element. Yep. I just have to take care that k is one indexed. Yep. And array index begins from 0. Okay, that being said, let me get the zerist implementation. Okay, so this is it. So I first resort the array, mutate array. Yep. And in descending order, then I return the k minus 1 element. Yeah. Good. And I submit my code and accept it. Okay. So for this solution, time complexity should be over n log n, assuming that there are n elements in the nums array. And for space complexity, it should be O of n. So because in Python, the sorting is the temp sort internally, and it consumes O of n extra space. Okay, so this is my first approach. So I will introduce the second approach. And I'm pretty sure that this is the most famous approach for this kind of case largest spore questions. Okay, so I will quickly show how it works. So basically, I will use the mini heap. And I will scan each element in nums array. And firstly, I push it in the mini heap. The 3 is pushed into the mini heap. And then um, if the size of the mini heap is equal to k or less, I can just keep it in the mini heap. Yep. And I will take a look at another element 2, and again I push it into the mini heap. Yep. And the size of the mini heap is still 2, which is equal to k. It's okay. And when I take a look at the 1, I push it into the mini heap. Then, because the size of the mini heap is 3, which is larger than k, 2, so I pop out one element. In this case, because this is a mini heap, I pop out 1. Yep. Next, I will take a look at 5, and I push 5 into the mini heap. And because the size is 3, which is larger than 2, I pop out one smallest element, which is 2. So now I have 3 and 5. Yep. So in this way, I can always keep the k largest element in the mini heap while traversing. And once I finish scanning the nums array, there are k element in the mini heap, and I will pop out one element from that, which is exactly the kth largest element. In this case, second largest element. I will quickly show it to you. So for 6, I push it into the mini heap, and I pop out 3. Then when I scan 4, I push it in the mini heap, and I pop out 4. Then next, I pop out 6. Yeah. And this, no, sorry, 5, because this is a mini heap, and this should be returned. Okay. So in this way, I can solve this question with n-log k time complexity, because firstly, I scan each element in the nums, so there are n steps. And for each step, what I do is push it into the mini heap, which is size k, and after that, pop out for the mini heap optionally when the size is k plus 1. So basically, for each of these operations, the time complexity should be log k. So I multiply n and log k, and I get n log k time complexity. And for space complexity, all the data structure which I need is, mini heap, which is the size k, or k plus 1 at max. Yep. And I don't use any more extra non-constant space. Yep. Okay, so that being said, let me start the implementation for this. Okay, so this is it. So, yep, I iterate each num in nums in line 29, and I firstly push it in the heap in line 30. And then, if the size of the heap is more than k, I pop it out. Pop out the smallest element. And after this line 32 operation, the size of the mini heap should be always k. Yeah. Okay. Then in line 34, I confirm that there are exactly k elements in mini heap. Then I pop out the smallest one from that and I return it, which is exactly the Kth largest element. Okay, let me execute my code. Good, accepted. Okay. So now I will introduce the third approach, which is a bit more advanced. So now I will talk about the quick select. Okay, so for this approach, so I use a kind of technique which is named partitioning. And I will do that partitioning recursively. So you can think of this as recursion and partitioning. Okay. So let me talk about it. So let's think of this example. So firstly, I will talk about partitioning. With partitioning on the array, so what happens with the partitioning is that I will pick one pivot number, something from the array. And then after the partitioning, that pivot number should be at the position where that pivot number should be after the array is completely sorted. So that's where the pivot number should be. And aside from that number, for other numbers, all the numbers which is greater than or equal to the pivot number should be after the pivot number. And all the numbers which are smaller than the pivot number should be before the pivot number. So this is it. Okay, so this is the partitioning. Yep. I will talk about how I can do it while the implementation. But anyway, this is the partitioning, and in my quick select approach, I will do this recursively. So let's say I'd like to return the second largest element. So because there are 6 elements, the second largest element should be fourth smallest element. In 0 index. Okay, for convenience, I did this conversion quickly. Yep. Okay, so, and that being said, my task is to find the first smallest element, which should be here, which comes here. So once I did the partitioning in this way, I take a look at the pivot number's position, which is index 3, and I find that I'd like to find the fourth smallest element, which is greater than the pivot number. So I will do that partitioning in the latter half. And fortunately, if the pivot number's position is exactly the fourth smallest element, then that's the end of the recursion. And even though it isn't the case this time, if I'm looking for the first smallest element and the pivot number is at the index 3, I will do the partitioning in the first half. Yeah. So in that way, on average, the range I have to take care becomes half and half and half. Yeah. So in that way, I will take care of this region and pivot number should be somewhere. Yeah. And I will continue that. Okay. So in this case, let me think. For example, if I pick the 2 as the pivot number next, and if I do the partitioning, let's say I find the pivot number 2 at the second position. In this way. So, fortunately, the pivot number is now at index 4, which is exactly what I'm looking for. No pun intended. Okay, so I can return this 2. No, sorry. Case, because I forgot to do the partitioning here. So, let me see. I get 1, 2, 2, 1. So it should be something like this. So this example isn't so good. Firstly, if there are too many numbers, let me quickly change it. Say I'm looking for the second largest element, which is third smallest element. And in this example, for say I guess the 3 as the pivot number, then 3 comes here. Then 2 and 1 should be here and here. Then 4 and 5 should be here and here somehow. Yep. So now, because pivot number 3 is index 2, and what I'm looking for is the index 3, I will take a look at the latter half and say I pick 4 as the pivot number. So in that case, 4 comes here. Yep. So in this way, I find the third index 3 as the pivot number, so I can return 4. So that's how it works. Okay. And for time complexity, On average, in a very normal case, let's assume that the pivot number is at the center position, always. The pivot number comes here, and in the worst case, I have to take a look at in the worst case, the index I'm looking for never matches the pivot until the last, until the end of the end. So in that case, I find pivot number somewhere. In this way. Yeah. So the scope kind of range, which I have to do the partitioning, becomes half by half in every recursion. Yeah. And let me think how many times do I have to do the recursion. Because the range becomes half by half, it should be log n times. And for each, oh, sorry, let me take a look at it in another perspective. Firstly, I will take a look at n partitioning. And I have to do the partitioning for n numbers, n element. Then n out of 2, then n out of 4, n out of 8, blah, blah, blah. So in total, it should be 2 times n. So the time complexity should be on average O of n. Yep. I think I should implement this before I'm talking about the space complexity because it could totally depends on the implementation of the partitioning, which I haven't shown yet. So let me start the implementation. So this is the index I'm looking for. Then, that being said, I will do the partitioning. Okay, so from here, I will implement the recursive function. So firstly, I will pick up the pivot number. So let's say the pivot number is the last element in the range. Yep. Oh, sorry. And the recursive function should have the range, or I should say the scope, because the scope should be, as I said, on average, becomes half by half. So I have to keep track, which is the range I will look for. Like this. Okay, so this is it. And I actually don't have to pass nums because it's globally accessible in this find the Kth largest method. Okay. So as I said, I pick up the pivot number as the last index. So this is what I've done so far. The 3 is the pivot number. And the low is here and the high is here. Okay, so now what I will do is I will use the 2 pointers, writer and reader. So I move the reader, and if the number as a reader position is smaller than the pivot number 3, then I swap reader number and the writer number, and I move the writer pointer. So let me show it in this with this example. So let's say something like this. Let's say writer should be index 0 and the reader moves from index 0. Now reader number is 2, which is smaller than the pivot number. So I just have to move the reader pointer. And then now reader number is 4, which is larger than the pivot number. So I swap reader and writer. Then I move the writer pointer. So in this way, sorry, let me do with this example. So I should say, if reader number is smaller than the pivot number, because the smaller number should go to the first half, I swap it with writer pointer number. In this way, then I move the writer pointer. Okay. And I will take a look at the next reader number, which is 5, which is larger than the pivot number 3. So I just have to move the reader pointer. And now I find that the reader is 2, which is smaller than the pivot number 3. So I swap reader and writer. Then I move the writer pointer. And this is the end. Yeah, reader number should be take a look at each number before pivot number. Yeah. So in this way, as the consequence, every element which is before the writer number should be smaller than the pivot number. So in the end, I will swap the writer number and pivot number. Yep. So in this way, I find that every number before pivot number's index is smaller than pivot number 3, and every number which is later than the pivot index is larger than the pivot number. In this case, they're sorted, but maybe this can be like this. It depends. But anyway, this is the implementation of the partitioning. Yep. So let me implement this. Okay, this is it. So the next thing I will do is to swap writer number and pivot number. Yep. And then you know, I the pivot index should be exactly the writer index currently. Okay. So wait, I think I I can use the nth index I'm looking for with just global index. So what I mean to say is this index is I'm looking for. And I can completely forget to pass this because this target index is accessible even in the find method. So here, I can do it in this way. And if the target index is before the current pivot index, I have to take a look at the first half. Otherwise, because the pivot number, no, target index is later than the pivot index, I have to take a look at the latter half. In this way. Sorry. Okay, so this is the implementation of partitioning. And I'm pretty sure I finished the implementation. Okay, so let me execute my code. Oh, accepted. Wow. Wait. Okay, time limit exceeded. So let me tell you why. But before that, I will quickly take a look at the complex analysis. For the space complexity, on average, the space I use is only the recursion stack. So in the worst case, on average case, there are log n recursion stack. So it should be log n. So this is the average case. However, I have to think of the worst case. Okay. So in the worst case, let's think that the number is sorted like this. And every time in my current implementation, I pick up the last element as the pivot number. So in this case, 6 is the pivot number, and this pivot number ends up with the last index here. So I will do the search in the first 5 element, and then 5 is chosen as the pivot number next, because I choose the pivot number. I choose the last element in the scope as a pivot number. Then it ends up in the position, last index in the current scope. So my pivot scope, my next scope is, I have to take care of the one element smaller scope. So in that way, so in total, I have to do the partitioning for n element, n minus 1 element, n minus 2 element, blah, 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 3 element, 2 element, 1 element. So in total, it should be n times n plus 1 divided by 2. So it takes n squared time in the worst case. And for space complexity, in the worst case, there are n recursion stacks. So the worst space complexity should be O of n. Okay. But there is a way to avoid this worst case. There are 2 techniques. The first technique I can use is don't pick the last element as a pivot number every time. Instead, I will pick the random number out of the current scope and use it as a pivot number. So in that way, I can reduce the possibility that, it becomes worst case. Yeah. Unfortunately, every time I choose the biggest number out of the current scope, it takes n squared time. But I can just say I can reduce the probability, that it comes through. So what I can do as optimization is I do something like this. So I choose the pivot index randomly from the current range, and I swap that pivot number with the last element. Because if I do that, I can use the implementation I've done in line 88 to line 95. So this is the first optimization. And I will try to submit my code again. But I know that it actually ends up with time limit exceeded. And let me tell you why. So in this case, you can find that there are so many same elements like this. In this case, what happens is that whichever index I choose as a pivot index, pivot number, let me see. So I swap this with the last element, And then what I will do next is to, okay, sorry. Let's say I'm looking for the second smallest index. And if all the numbers are the same, what happens is that I choose the pivot number 1. And because this is the last element, yeah, what happens is that when I do reader-writer swapping, I find that this number 1 is, equal to the pivot number. So I don't move it, don't move it, don't move it. And writer never moves. And it ends up with, reader traversal ends, yeah. Okay. So after that, oh, sorry, let me say, I'm looking for this index. Yep. So because reader didn't move, the pivot index should come here. Yeah. And the remaining scope becomes this. And let's say I choose some number 1 from the pivot, and swap it with the last element. And still 1 is the pivot number. So the same thing happens. So reader moves, but reader writer numbers are never swapped, and reader ends the traversal. Then pivot number, sorry, I start with this here. So I find that the pivot number is now here. So this is my remaining range. So in this way, yeah, oh, sorry. Oh, wait, yeah, this is correct. So I can say, no, actually, the last element is never excluded from the scope. So what I mean to say is, if there are so many same numbers, whichever number I choose the pivot number, the remaining scope is reduced by 1, only 1 size. Yeah, because as shown in this example, only the first element in the current scope should be popped out. Reduced. Yeah. So there are n times of recursion. And to avoid this, so what I can do is, so in my current partitioning implementation, in line 104, if the reader number is smaller than the pivot number, I do the swapping. But if reader number is equal to the pivot number, no swapping every time. But I change the implementation so that if reader number is equal to the pivot number, half of them should be put before the pivot number. Yeah, eventual position. And half of the numbers, which is equal to the pivot number, should be put later than the eventual pivot number's position. So in that way, even for this case, yeah, the number of element, I mean, the size of the scope is reduced by half. So that's the optimization I can make. So I use the frog here. Okay. So if radian number is equal to the pivot number, in 50% probability, reader number and writer number should be swapped. Okay. So let me execute my code. Good. And I submit my code and accept it. Great. So in this way, in the case like this, I mean, so many same numbers case, I could avoid that the time complexity becomes n squared. Yep. Okay, so now I will implement the fourth approach, which is counting sort. So this is a kind of, tricky way. And I can use this approach because in this case, all the numbers are integer. So when the number is integer, the you know candidate of the nums is limited. So that's a key in the requirements that I can use the counting sort. So for example, in this case, the first thing I would do is think of the mini number and max number in this nums. And they're 1 and 6 in this case. Next, I would prepare the kind of plot for each candidate nums from 1 to 6. Then I will take a look at the nums array one by one. And if number appears, I increment slot 3. So you can think of this slot as the kind of frequency array. Let me tweak a little bit. Then when I get 2, I increment the count of number 2. Then for 4, I increment this. And for 1, I increment this. And for 3, I increment this. Oh, by default, all should be 0. And for 6, I increment this. And for 4, I increment this. And after building the frequency array by traversing all the numbers in the nums, I count it from the head. So if I'm looking for the fifth smallest element, I count the nums, and once I find that the, you know, here I find that, oh sorry, so here because there are only one element, this number 1 should be from index 0 only. And for this 2, this should be 1 to 1. So exactly index 1, when nums are sorted, is 2. And here, you can say the second and third index in the sorted nums array are their num3. Yeah. Then I find this and this. So index 4 to 5 in the sorted nums array, those elements are number 4. And because I'm looking for the fifth smallest, I return 4. Yeah. And that's it. So this is the approach I can use by the counting sort. So for space complexity, it should be like this. I traverse each element and firstly I have to initiate the max num minus min num array. Then I traverse an element and I put it in the frequency array. Then I have to, do kind of line sweep on the frequency array, which takes max num and min num. So this is the time complexity. For space complexity, it should be max num minus min num because that's the size of the frequency array. But actually, I can use instead of frequency map. Yeah, I don't have to initialize each element. Sorry, with size, this size. If number appears, I just have to create a new key in the frequency map and then increment the count. So in this way, space complexity should be this. So as I can see, basically in the worst case, if all the numbers are, yeah. So because they're up to n element, that frequency map never becomes larger than n. And if the numbers are, duplicated, like 1, 1, 2, 2, 3, 3, then 100, in that case, I don't need n space. I mean, frequency map doesn't have n element. It's just the number of unique element in this scope. Yeah. And in the worst case, the number of unique element in that scope should be max num minus min num. So that's space complexity. Okay. That being said, I will start the implementation. Oh, let me separate it into the sum method. And I will do something here. So from the frequency map, I can find how many number of nums there are in this array. But if the current number doesn't exist in the frequency map, I just have to skip. Okay, and then I guess the num count. So with that num count, I can find the index range of the current num in the sorted nums array, just like line 132. Yep. If there are one element, oh, it should be -1. If there are two elements, current index high should be next into +1. Good. Okay. And if the target index in this is in this range, I will return current num. And after that, I will remove the next index. Like this. Good. Okay, so now my final task is to implement the build frequency map. Okay. Okay, it becomes like this. Good. So now I submit my code. Oh, great. Now it looks okay, so submit. Great, accepted. Okay, so I introduced all the four approaches. So let me quickly review my video and let's call it a day. Okay, so in my today's video, I picked up the question, Kth largest element in an array. So in this question, I'm given an integer array nums and I will return the Kth largest element in the array. And I introduce four approaches. The first approach is sorting. Yeah, I firstly sort the array in descending order, and I just return the case element in the sorted list. That's the sorting approach. And the second approach, many have of size k, which is the most famous approach for this kind of question. So in this approach, I traverse the nums array and I push each element into the mini heap. And if the mini heap exceeds the size k, I pop out the smallest element from the mini heap. In that way, I can always keep track of the largest k element while traversal. Then after the traversal, I pop out the smallest element from that heap and I return it. It is exactly the kth largest element in an array. Yeah. And the third approach I introduced was the quick select. In this approach, I did partitioning recursively. Yeah. And as I said, in the naive implementation, the time complexity was average over n, but in the worst case, n squared. So I introduced two optimization techniques, and I could avoid the worst case. I mean, I could reduce the probability of the worst case n squared. Yeah. And I could, made my solution work. And the last approach, counting select. So this worked because this is the integer array, which means that the candidate of element in nums array is limited. Yep. I created a kind of frequency map. And firstly, I traverse the array nums and builds the frequency map. And the next thing I did was to take a look at each possible candidate number from the smallest one to the largest one in ascending order. And every time for each number, I can know how many elements there are in the original array. So with that, for each number, I can say in a sorted nums array, index which to which should be that number. Because I know that, is the target index I'm looking for is exactly in that bucket. Yep, that's the number I should return. So that was it. Okay, so being said, I finished my today's live coding session. Thank you so much for watching.